Right. Well, thank you very much for the possibility to speak here. Well, when I heard about values, I thought, well, values can change in mathematics, can't they? And when I think about change, I think about Lakatosh, and so I wrote something less than 400 words called a Lakatosian approach to value systems for this conference, and then I did something else. And then I came back to the talk, and I was looking for examples where values change. Now I'm interested in set theory, so set theory was the way to go to, or what I wanted to go to. And well, in set theory there is lots of work done on extending our theory of sets, so the search for new axioms. Now there must be some values in there, I thought, so I had a look at it and looked for a nice story, a nice example. And I found a very good story, a very nice example, a story I really like. So I worked on this and worked on this and worked on this, and then I wrote this talk, and I realized, oh, the story is too long. Basically meaning that I will lose out on a lot of this Lakatosian approach. So I was in a pickle, I didn't know what to do, and I chose the romantic way. I just like the story too much, so I'm going to tell you the story, and have some Lakatosh around it. The Lakatosian theory will be underdeveloped. Okay, so what I want to do is I want to tell you a story about Hugh Woodin. Hugh Woodin is one of the greatest set theorists of our time, and I want to tell you the story about how he changed his mind. Okay, so what I realized when I looked into this is that I wasn't really looking at values as such. I was looking at things that he valued, and they somehow changed. So I was looking at what I call value-laden ideas in this talk. And so value-laden ideas and how we value these things then changes. Okay, here's the outline of the talk. First of all, I'm just going to briefly talk about Lakatosian research programs. After the preliminary remark, I go into the main story of this talk in two parts, and there's a missing piece which I then discuss at the very end. And there's a theoretical thought in there. Okay, Lakatosian research programs. Well, I guess you know Lakatosh. Lakatosh has the idea of, well, he developed this in the philosophy of science, and it's the idea of making methodological assumptions unrefutable, making assumptions unrefutable by a methodological decision, and collecting them in a hardcore. So these are unrefutable assumptions. Now this hardcore can then conflict with some form of reality in some way, and we have to protect it. And we do this by additional assumptions, which we then collect in the protective belt. However, Lakatosh does not only put these protective assumptions in the protective belt, but everything that can change in our system. So changeable belt would have really been better rather than protective belt, but I'm just going to stick to the Lakatosian original here. So we have unrefutable assumptions in the middle. Around it, in a sense, we have the changeable assumptions. And how do these things change? Well, this is what our heuristic tells us. How does this change go about? Now, the idea for Lakatosian value systems was to put into the hardcore and the protective belt these value-laden ideas, or things that we value, and have a look at this. And well, this is what I do, this is what the story is all about. So a very brief preliminary remark. Woodin is a die-hard Platonist, a non-pluralist Platonist. What is Platonism? Well, Platonism is just Platonism. Non-pluralist is he in the sense that he believes that there is one true universe of sets. Yes, we're doing set theory, and so he believes in one true universe of sets. This is opposed to the pluralist conceptions of sets, which could be some form of formalism. But there's even pluralist conception of Platonism. Joel David Hampkins is the most famous proponent. If you want to know more about all this, then I would recommend the papers by Peter Kroner, which you can find on the Stanford, which talk about this pluralist, non-pluralist conception there. Okay, Woodin is a non-pluralist Platonist, and in that he is somehow classical. You can attribute this non-pluralist Platonism to Cantor, to the Melo, so he is in some sense a very old-fashioned Platonist. And we are going to join him in his research program. We are going to be non-pluralist Platonists for these 20 minutes. Okay, my story begins with how an open problem changed logic. Now I'm just going to take it as false value that we value classical logic. Yes, we use classical logic in mathematics in our endeavors, and we put a certain value into it. However, this then becomes changed by an open problem, and an open problem which is very famous, the continuous hypothesis. Okay, as you all know, set theory, as by its axioms Z of C, cannot resolve the continuous hypothesis. It's independent. That's a method that's shown by Cohen's method of forcing. But the question is still interesting to mathematicians and to set theorists. And well, approaches were to restrict our subsets here, so look at closed sets or open sets or Borel sets and so on. For all those, the continuous hypothesis holds. But in this whole discussion of the continuous hypothesis, there were connections realized to descriptive set theory, and in all of this discussion emerged a new axiom, which is called projective determinacy. Now, there has been some papers, some work on projective determinacy, which explains this philosophically. Peter Körner, again in Stanford, is one example. There's definitely not enough, as I discussed yesterday with Jose. Yes, I'm just going to take it as face value, like Woodin does. Projective determinacy has been accepted as a new axiom. Now, projective determinacy, we can't prove projective determinacy from our axiom system Z of C. In fact, it increases consistency strength. So what does that mean? The consistency of Z of C plus projective determinacy implies the consistency of Z of C, but not vice versa. So this is stronger. Okay, Woodin takes this as face value and says, oh, okay, this is it. He talks a bit about this in his 2001 papers on the continuous hypothesis. And what he now argues is that he can do an incremental approach to the continuous hypothesis problem, to the continuum problem. So he looks at these structures here, H of omega epsilon. What is H of omega? Well, in H of omega you have all the sets whose transitive closure is less than omega, so all finite sets are here. Now this is just first order number theory. Well, for first order number theory, the axioms of Z of C are generically complete in the sense that by Cohen's method of forcing, you cannot show the independence of any statement about the structure here. So this is some good form of completeness. Yeah? Obviously, Gödel's results say this cannot be complete, but it's generically complete. It's nice. It's a nice completeness. It's complete enough. Right? Now, in here, this is just second order number theory. If we accept the theory Z of C plus projective determinacy, we get something very similar to this generically completeness. For our theory is similar to being generically complete. Similar in the sense that we can't prove that it really is, but we just don't know any counterexamples. Which is good enough for Woodin. So we can have a theory which describes this structure very well. Now we have a theory which describes this structure very well. And if we now realize that in this structure the continuous hypothesis becomes decided, well then we just want to find a very good theory for this one. Yeah? So we want to extend our theory of sets so we find a nice axiomatization for this. Well, the problem is that we are now looking for a new axiom. How do you do this? Well, actually this is really complicated. And not even large cardinal axioms decide the CH. I'm going to talk about large cardinal axioms in a second, but this just amplifies the problem. And what Woodin then does is, well, we just extend to a stronger logic. Now, there must be some argument here, one thinks, but there really isn't. I'll give you the quotation. My point is simply that the axioms we seek, so the axiom for this structure here, cannot possibly be implied by any consistent large cardinal hypothesis remotely related to those currently accepted as large cardinal hypotheses. Next section begins, strong logic. The solution is to take an abstract approach. This we shall do by considering strengthenings of first-order logic. This is what he says in 2001. So what happens here is that we have this value-laden idea of classical logic, plus a certain value we put into a solution to this continuum problem. Yeah. And somehow in 2001, Putin is convinced that it tips the balance. Yeah. So he is willing to discard classical logic and favors a solution to the continuum problem. Now he then develops omega logic, which is a strong logic, and it's a respected area of research. People are writing their PhD thesis about omega logic currently, and definitely interesting. And then he gives us, using omega logic and the omega conjecture, and there's lots of mathematics now going on, but he has extended logic. Yes? And with this extended logic, he now does very much mathematics, and then gives us reasons to believe that the power of the continuum is actually Alf2, so that the continuum hypothesis is false. And this is implied by his famous star axiom, Woodin's star axiom. This is this he presents in 2 papers in 2001, and then re-elaborates on it in a paper in 2004. Okay, this is how he thinks about extending set theory. And now we come to the second part of the story, where he now changes his mind. This story happens in 2009, 2010, 2 papers in 2009, 2010, and we need just a little bit of large cardinals. Yeah? What are large cardinal axioms? Those are strong axioms of infinity. So what do they say? They say there is a set that has certain properties. Yeah? Now they are all stronger than ZFC, meaning that they increase consistency strength. So we cannot prove that these sets exist, but these properties are nice. Yes, that theory is valid. Now what makes these large cardinal axioms so very interesting are 2 facts. For one, they are linearly ordered by consistency strength. So the consistency of a huge cardinal, so ZFC plus there is a huge cardinal, implies the consistency of ZFC plus there's a strong cardinal, for example. Now this is one fact. The other fact is that you can take virtually any statement of set theory, which is unsolvable from our axiom system, and translate it into a large cardinal hypothesis, meaning that if this is consistent, then also the other statement is consistent with our axiom system ZFC. So what this does, these 2 facts give us together, we take a statement here, and then a seemingly completely unrelated statement in set theory, which is over here, and we can now bring them into the large cardinal hierarchy, but these large cardinals are then comparable by their consistency strength. So this gives us, in a sense, an order of unsolvability. Yeah? How difficult are these problems? How far away from our axiom system ZFC are these problems? How unsolvable are they? Right? So these large cardinal axioms are really somehow central, and in fact mathematicians who work on this, on extending ZFC, work on large cardinal axioms because of this centrality. The problem is, well, we cannot show their consistency, right? So how to argue for their consistency? If we want to make the case that ZFC should be extended by there is a strong cardinal, well, we want to at least that this is consistent. How to argue for the consistency? One approach is the inner model program. Now the inner model program goes a bit like this. This is going to be a picture. You might have seen this picture of the universe of all sets. There are some dots up here because it goes absolutely without bounds. All the sets are in here, and here are the cardinal numbers. And we call this universe of sets V. Now what Gödel did was he constructed an inner model called the Gödel's constructible universe called L, which is probably the smallest inner model of ZFC, and it is very nice. We can understand it very, very well, but it does not accommodate any large cardinal axioms. So, well, this is the problem for people like Woody, who really like large cardinal axioms. They really want them. So how to account for their consistency? The idea is to extend L in a sense, to make a bigger L, which can then accommodate large cardinal axioms. But yeah, how to do this? This exactly is the inner model program. So what you do is you assume that the large cardinal axiom is consistent, and you then give a construction of the model. So this is no consistency proof. I mean, we cannot prove their consistency in a strictly formal way, but it gives us a very good argument. Colin has put this as, this is a delicate argument. I really like this. A delicate argument for the consistency. Now, and what then happens is we get a somewhat bigger model, somewhat fatter model, and these fatter models then can accommodate large cardinal axioms. So where are we? Well, we're somewhere up to here. Now there are some subtleties in there, which is why I don't give you the precise thing where we are. But the inner model program has reached this level here. So how has it done this? Well, it kind of went step by step using one large for one large cardinal axiom you get this inner model, and then once you have this, you expand to a new one, and it becomes incredibly more complicated. And then you do the next step, which is even more complicated. And it's been going on for a long time, over 20 years now, and we have reached this level here. In fact, our best approach to this are the Mitchell-Steele models, and they cannot reach anything stronger than a super strong. Okay? So these super compact are kind of out of reach for us at the moment of this inner model program. Now, what Woodin does is Woodin dreams a bit. And Woodin thinks, oh, what would happen if we would actually reach a super compact? Yeah? Well, what then happens is this theorem. Don't worry about the mathematics behind all this. What it says is, if we can reach the supercompact level, then we get an ultimate enlargement of L. What does that mean? We could accommodate all large cardinal axioms. Virtually all, because Reinhardt cardinals are the ones at the top are more difficult. But we can accommodate virtually all large cardinal axioms. This, if we reach the level of a supercompact, then this is not limiting in any way. Okay. Well, we do not know that we can actually do this. Okay. And in 2009, he presents this theorem that we can, if we could, then everything would be great. In 2010, he proposes an axiom. Again, don't worry about all the mathematics in there. So he proposes an axiom which he thinks is the axiom that V is ultimate L. So that there is actually this ultimate enlargement, this model which we know about, the structure we know about, which can accommodate all large cardinal axioms. Now, as I said, we cannot prove that it does, but Woodin really thinks that it does. He's hoping that this model here can then accommodate all our large cardinal axioms. And this will have to be validated by further research. Now he obviously has done a little bit of research, and this is what he writes in 2010. This axiom here implies the continuous hypothesis as well as the omega conjecture, and will arguably reduce all questions of set theory to axioms of strong infinity, and so banish the specter of undecidability as demonstrated by Cohn's method of force. Okay. Now, a few minutes back, I told you that Woodin has this argument, yeah, which he presented in 3 papers throughout the years 2001 and 2004, where he says that the continuous hypothesis is actually false. Right? He gave us this argument why it is false. Now he presents a new axiom, well, which implies the continuous hypothesis. He's changed his mind about this continuous hypothesis. So there's certainly a change of mind, but there's something something going on here in this lower part, which I think is one of the reasons why he does this, why he proposed this new axiom. He talks about banishing the specter of undecidability as demonstrated by Cohn's method of forcing. Now, I told you about this non-pluralist hardcore of Woodin, the non-pluralist Platonism. The pluralist conceptions, so the rival conceptions, our rival programs, they are closely connected to Cohn's method of forcing. What does Cohn's method of forcing do? Well, if you have a model which, if you have a universal set, then you can extend it by Cohn's method of forcing to get a new model, which could then also be this is also a new universe. And the pluralist conception says, well, these could all be acceptable universes. This obviously is oversimplified, but it is very, very strongly connected to forcing the pluralist conception. So, what Woodin does here with this axiom, well, if he really can banish the specter of undecidability, or how he also calls it, ending the age of forcing independence, then he would thrust at the stronghold of his rival programs. He would thrust at one of the fundamental ideas or concepts, Cohn's method of forcing, and attack his rival programs right there. Now, he hasn't won yet. This is an ongoing debate. It's a debate that's going on right now. And I think it's a very interesting debate, how this will develop. Okay, so this ends my story about how Woodin changed his mind. Let me very briefly say something about the heuristic, which has been the missing piece in this talk. I've been giving you the hardcore of the value system. I've been talking about how things changed, so about the protective belt, the story about the protective belt. Programs consist of three pieces. The missing piece is the heuristic. Now, heuristic principles have the form that in case of A, then C, B causes, roughly. Now, in this case of value systems, we have that, well, or in this case of value-laden ideas, that A events have the form that X competes with Y. So our urge to solve the continuous hypothesis competes with classical logic. And then B just becomes, well, there's a competition. This is boring. What we really want is that the heuristic kind of tells us how to resolve this competition. So what we have is, we have two value-laden ideas which now compete with one another, and we want to find out how to resolve this. Now this is certainly a difficult issue, and I doubt that this can be done with a proper logic behind this. Yeah? So what I would propose is that the heuristic contains a variety of angles of attack, which may change the values of X and Y. What do I mean by angles of attack? Now, again, the continuous hypothesis and classical logic. Now, we wanted to solve the continuous hypothesis or the continuous problem very early on. I mean, Cantor started this. This is over 100 years old, this problem. And then Cohen came along and showed, well, you can't resolve this in our current theory of sets. In ZFC, you cannot neither prove nor disprove. It is independent of our theory of sets, which then gave maybe not rise, but further credit to pluralist conceptions of that theory. So our rivals had somehow resolved the whole continuous problem issue, because they could just say, well, it really depends on the universe you're in, whether the continuous hypothesis holds or not. So all of this increases our urge to solve the continuous problem in our non-pluralist Platonist conception, right? So there's thrive upwards. On the other hand, we have classical logic. It seems to me that our study of non-classical logics might have influenced our value we put into classical logics. I haven't talked about this too much, okay? But I think an idea of familiarity with non-classical logics comes into play here, where somehow this value we put into only true classical logic might diminish a bit. So we have this balance, and then at some point the balance tips. So the urge to solve the continuous problem topples our value in classical logic. Okay, very last remark in this picture. What about beauty? Beauty has been one of the topics here. Now, I think in this picture, beauty now becomes a heuristic principle. Now, that means it's program dependent, and beauty could change values of x and y. Now, this is certainly not very Lakatosian. Lakatosh wanted to have logic in his heuristic. It was all about rationality. And now to have beauty as a heuristic principle, well, that doesn't seem very Lakatosian at all. Well, I guess that just shows that I'm willing to change Lakatosh where I think that he needs changing, because I think he needs changing at some points. And this might be one of them. Actually, the very first talk gave me a wonderful citation, which I'm just going to read out again. We heard this this morning. It's from Kalmar, and it goes, there are no mathematicians, however abstract the subject matter might be, for example, the stuff I've been talking about, who do not think intuitively, heuristically during their research. Subsequently, they would cast their results in axiomatic form, thereby camouflaging how they arrived at them. Yes, so a form of heuristic and intuition, that these two things go together. I found this very beautiful. Yes, Woodin, on the other hand, Woodin does not talk about beauty. Woodin is a diehard Platonist. He's looking for truth, right? He's looking for the one true axiom for set theory. In fact, the only value-laden language he uses is remarkable. At one point, his theorem that if you go up to the supercompact, then you get the ultimate L. That's, according to him, a remarkable theorem. Everything else is, everywhere else he doesn't use any value-laden language whatsoever. Yes, so I guess if we want to make this work, the value systems in the Lakatosian approach, we have to change Lakatosian methodology of scientific research programs accordingly. But I think we have to change it anyways to say something new and hopefully interesting.